What if the universe's most fundamental ingredients aren't tiny specks of matter like miniature marbles? Instead, picture everything being built from incredibly small, energetic strings constantly vibrating like the strings on a microscopic guitar. Sounds pretty wild, right?
It does sound wild, but that's the core idea behind string theory. And it's a truly mind-bending attempt to provide a single description for everything we know about the universe.
A single description, like the ultimate theory.
Well, that's the hope. See, we have our theories that work incredibly well for the very small, that's quantum mechanics, and our theory that beautifully describes gravity and the vast cosmos, Einstein's general relativity.
Right, the big stuff and the small stuff.
Exactly. The problem is these two frameworks, they don't quite mesh perfectly. They don't really talk to each other properly. String theory offers a potential bridge, a way to connect them.
Okay, so instead of thinking of electrons or quarks as these little points, string theory says they're actually these tiny wiggling threads of energy.
Precisely. Minuscule energetic strings.
And here's where it gets really fascinating for me. Just like a guitar string vibrating in different ways produces different musical notes, these fundamental strings vibrating in different patterns could actually be different particles. Like one vibration is an electron, another is a photon.
That's exactly the idea. It's like the universe is a grand symphony played on these tiny vibrating strings. The way a string vibrates dictates its properties, like how heavy it is, its mass, or its electrical charge, things like that. This offers a completely fresh perspective, suggesting that what we see as different forces and particles are actually just different manifestations of these fundamental vibrating strings.
So it's all just different music from the same basic string.
You can think of it that way. Like the different instruments in an orchestra, they all produce sound through vibration, but the different ways they vibrate create this rich tapestry of music. String theory aims for a similar underlying harmony for the cosmos.
Now, when you first hear string theory, you might think, okay, one theory. But it turns out there are actually several versions, right? Like different ways to tune the cosmic guitar.
That's a fair analogy, yeah. There were initially 5 main consistent versions developed, type I, type IIA, type IA, and 2 heterotic types. They explored different ways these strings could vibrate and interact.
5, okay, that sounds complicated.
It was. But a really exciting development came later. The realization that these seemingly separate theories might actually be different facets, different viewpoints of a single, more fundamental idea. Something we call M theory. We can definitely circle back to that in our deep dive here on Cosmic Origins Revealed.
M theory, okay, filed away. But let's tackle another really strange part first. This whole dimension thing.
Yes. The extra dimensions.
String theory's math only seems to work if we assume there are more spatial dimensions than the 3 we know, plus time. We're talking 10, maybe even 11 dimensions. Where are they?
That is the million-dollar question. The leading idea is something called compactification.
Compactification. Sounds like packing a suitcase.
Sort of. Imagine a garden hose.
Yeah.
From really far away, it just looks like a one-dimensional line, right?
Yeah, just a line.
But get up close, and you see it actually has a second dimension in its circumference, curled up really small.
Ah, I see. Okay.
String theory suggests that our familiar 3 spatial dimensions might be like the long length of that hose, while the extra dimensions are curled up incredibly tightly everywhere, at every single point in space, but far too small for us to see directly.
So they're everywhere, but just rolled up super small, affecting things, but invisible to us. Wow.
Exactly. They're still there, influencing physics at the most fundamental level, even though we can't, reach out and touch them.
And I think I read somewhere on Cosmic Origins Revealed that this isn't just a mathematical trick. The idea of extra dimensions actually leads to predictions, things scientists are trying to look for.
That's absolutely right. It's not just a quirk. The specific way these extra dimensions are folded or curled up their geometry can have a big impact on the kinds of particles and forces we observe in our large familiar dimensions.
How so?
Well, the geometry of these hidden dimensions could potentially explain some real mysteries in particle physics. Like, why do fundamental particles have the specific masses they do? Why is gravity so much weaker than the other forces? The shape of these extra dimensions might hold the answers.
This is already bending my brain. Okay, let's dig into that folding. We've got compactification, these dimensions curled up super tiny.
Right. And physicists believe they aren't just crumpled randomly. There are specific, very complex geometric shapes that seem to fit the bill mathematically. They're called Calabi-Yau manifolds.
Calabi-Yau manifolds. Okay, that sounds intense. Why are these shapes so important?
Their intricate geometry is, well, crucial. The precise way these manifolds are shaped dictates how the fundamental strings can vibrate within those curled-up dimensions.
Ah, okay, so the shape limits the vibration.
Exactly. And remember, the vibration pattern determines the particle properties we see. So understanding the geometry of these Calabi-Yau manifolds is like understanding the exact design of a musical instrument. It tells you what kinds of notes or particles it can produce.
That makes sense. The hidden shape affects the physics we actually measure.
Okay, another term I hear a lot with string theory is duality. What's that about? Sounds like two things being the same but different.
That's a very good way to put it, actually. In string theory, dualities are these deep, sometimes surprising connections showing how seemingly different versions of string theory can actually be mathematically equivalent. They're describing the exact same underlying physics, just from a different perspective.
Like looking at the same object from the front versus the side?
Kind of, yeah. Or imagine having two different maps of the same city. One might be a road map, the other a topographical map. They look different, use different symbols, but they both represent the same underlying reality and can guide you effectively. That's the spirit of duality in string theory. So those 5 different string theories you mentioned earlier, type I, type 2, etc., maybe they aren't totally separate after all, thanks to these dualities.
Precisely. That was a huge realization. These dualities show that the 5 superstring theories were intimately related. It turns out they are different limiting cases of that deeper 11-dimensional theory we mentioned, M theory.
Okay, so dualities help simplify things, in a way.
They're incredibly valuable tools. They allow physicists to take a problem that looks really hard in one version of the theory and translate it, using a duality, into an equivalent problem in another version where it might be much easier to solve. It's like having a Rosetta Stone for string theories.
A secret key. I like that. Now back to the dimensions. It's still so weird. Early versions needed 10 dimensions, you said.
That's right. For the math in both early Bosonic string theory and the later superstring theories to hang together consistently without breaking down, they required 10 spacetime dimensions, 9 of space, 1 of time.
Which is obviously a big jump from our everyday experience of 3 plus 1.
A huge jump. It was one of the most startling predictions of the theory.
And then M theory comes along and says, actually, let's try 11. What prompted adding another one?
Well, M theory emerged in the mid-1990s, largely through the work of physicists like Edward Witten. It wasn't just adding one for fun. It turned out that in an 11-dimensional framework, all 5 of those 10-dimensional superstring theories could be seen as different limits or different perspectives of this single underlying M theory.
So the 11th dimension was the key to unifying the 5 string theories.
Exactly. It provided this overarching structure. Think of it like discovering that mountains on different continents are actually part of the same underlying tectonic plate. The 11th dimension allowed physicists to see the connections, unifying the landscape. As we love exploring here on Cosmic Origins Revealed, it brought a lot more coherence to the whole picture.
So what are the really big consequences if these extra dimensions are real? Why should we, living our lives in 3 dimensions, really care about them?
Oh, the implications are potentially enormous. One of the biggest hopes is that these extra dimensions could finally allow us to unify gravity with the other fundamental forces, the electromagnetic, strong nuclear, and weak nuclear forces.
The theory of everything.
That's the grand goal. For decades, that's been the dream. A single mathematical framework describing all forces and particles. General relativity describes gravity beautifully. Quantum field theory describes the others. String theory, because it requires these extra dimensions, naturally incorporates a quantum description of gravity alongside the others. It offers a pathway.
That's incredible. Now, you briefly mentioned bosonic string theory needing 26 dimensions. That's way more. What was that about?
Right, bosonic string theory was an earlier version. It was simpler mathematically in some ways, but it only described bosons, the force-carrying particles like photons. And yes, its mathematical consistency demanded 26 spacetime dimensions. It had a major problem. It predicted particles called tachyons, particles that would travel faster than light and have imaginary mass. We don't see anything like that in the real world, so that was a big issue. It suggested the theory was unstable or incomplete.
So moving to superstring theory, fix that. The one with 10 dimensions.
Pretty much, yes. Yeah. Superstring theories incorporate something called supersymmetry.
Supersymmetry sounds important.
It is. It's a hypothesized symmetry between the 2 fundamental types of particles, bosons and fermions, matter particles like electrons and quarks. By including fermions and this supersymmetry, superstring theory not only got rid of the problematic tachyon, but also reduced the required number of dimensions down to a more manageable 10.
More manageable. Still 10. Okay, just to recap for everyone following along with Cosmic Origins Revealed. Strings are the fundamental bits. Tiny vibrating loops or open ends.
Correct. One-dimensional objects.
String theory tries to be the grand unified theory, explaining everything.
That's the ambition.
The way strings vibrate determines particle properties like mass and charge.
Exactly. Different notes, different particles.
There were initially multiple versions, later possibly unified by M-theory.
Right. Linked by duality.
And crucially, it needs extra spatial dimensions beyond our usual 3.
10 for superstrings, 11 for M-theory.
And the math involves some pretty heavy stuff like Calabi-Yau manifolds for those hidden dimensions.
Very sophisticated geometry and topology, yes. And we distinguish bosonic theory, just bosons, 26 dimensions, Tachyons, from superstring theory, bosons and fermions, 10 dimensions, no Tachyons.
Got it. So, just to nail it down, a listener might ask, how many dimensions, again, for that early bosonic string theory?
That one needed 26 space-time dimensions.
26. Wow. Okay, let's explore M-theory a bit more. You mentioned it hints at, well, a multiverse. Our universe being just one of many. That sounds like pure sci-fi.
It definitely has that flavor.
Yeah.
But it's a possibility that emerges quite naturally from the mathematics of M-theory, particularly in scenarios involving branes.
Brain, like membranes.
Exactly. Short for membranes. M-theory includes higher dimensional objects called branes. In some models, our entire 4-dimensional universe, 3 space plus 1 time, could be confined to one such brane, existing within a larger, higher dimensional space, sometimes called the bulk.
Okay.
And there might be other branes, perhaps parallel to ours, in that bulk. Each brane could be its own universe, potentially with different laws of physics. That's one way the multiverse idea arises from this framework.
So our universe is like a sheet of paper floating in a higher dimensional room, and maybe there are other sheets of paper in there too.
That's a decent analogy, yes. A truly mind-bending possibility.
How does this view of dimensions differ from classical physics? I mean, Newton and even Einstein seem to take 3 space dimensions and 1 time dimension is just stage fixed.
Right. In classical physics, and even standard quantum field theory, the dimensionality of space-time is usually an input, a fixed background. String theory is different because the number of dimensions is actually an output of the theory's consistency. The math demands these extra dimensions. They aren't just background. Their shape and size actively determine the physics we see.
So dimensions aren't just the container, they're part of the content.
In a sense, yes. And some interpretations even suggest time might not be as fundamental as we think, though that gets even more speculative.
Is string theory still where the action is? Is research ongoing? Are we getting closer to proving it?
Oh, absolutely. It's still a very active area. Direct experimental proof is incredibly difficult because the energy scales involved are likely immense, far beyond current particle accelerators. But research continues on many fronts, refining the mathematical structure, exploring dualities, looking for indirect cosmological signatures, or connections to potentially observable phenomena like properties of dark matter or cosmic inflation.
So no smoking gun yet, but lots of theoretical work.
Exactly. And the theory keeps generating fascinating insights, especially through its deep connections with mathematics. You mentioned Calabi-Yau manifolds and mirror symmetry earlier.
Yeah, the math connection seems really strong.
It's profound. String theory has actually motivated major developments in pure mathematics. Mirror symmetry, for instance, was a prediction from physics, a surprising duality between different Calabi-Yau shapes that mathematicians then proved and used to solve problems they couldn't tackle before. It's a remarkable interplay between physics and math.
And what about that wild thing I read about on Cosmic Origins Revealed, monstrous moonshine? That sounds completely made up.
It sounds fantastical, doesn't it? But it's real mathematics. It refers to this completely unexpected, seemingly bizarre connection between 2 very different mathematical objects. One is the monster group, which is the largest of the sporadic, simple, finite groups, a huge, intricate structure related to symmetries. The other is the J-function, a fundamental object in number theory related to modular forms. The coefficients in the expansion of the J-function seemed related to the dimensions of the representations of the monster group in this really weird way. Nobody understood why.
And string theory explained it.
Amazingly, yes. Certain formulations of string theory, compactified in specific ways, provided a physical framework where this connection naturally emerged. It acted as an unforeseen bridge between group theory and number theory. It's one of those things that makes you think there's some incredibly deep, hidden structure connecting different parts of mathematics and physics.
That's truly astonishing. Okay, one last technical term. Add CFT correspondence. I hear it's a huge deal.
It is. It's arguably one of the most important theoretical developments to come out of string theory in the past few decades. AD-SCFT stands for Anti-de Sitter Conformal Field Theory Correspondence. It proposes a duality, a mathematical equivalence, between a theory of gravity, specifically string theory or M theory, living in a particular type of curved spacetime called anti-de Sitter space.
Okay, gravity in a weirdly shaped space.
A quantum field theory, specifically a conformal field theory or CFT, that lives on the boundary of that spacetime. The CFT has no gravity and lives in fewer dimensions.
So a theory with gravity is secretly the same as a theory without gravity in fewer dimensions?
That's the mind-blowing part. It's like a hologram. The description of the bulk gravitational physics is encoded on the lower dimensional boundary. This correspondence is incredibly powerful. It lets us study tough problems in quantum gravity by translating them into potentially easier problems in quantum field theory and vice versa. It's given us new tools to think about black holes, quantum entanglement, and fundamental aspects of quantum gravity.
Wow, so it's like having two different languages to describe the same reality, and we can translate between them to learn more.
That's a great way to put it. It's a profound insight into the structure of physical theories.
It really is revolutionary, thinking that our universe might fundamentally be these tiny vibrating strings in, maybe 10 or 11 dimensions. It changes your whole picture of reality.
It's a radical shift, absolutely. And while we're still searching for that definitive experimental proof, string theory provides this incredibly rich, mathematically coherent framework that could unify everything we know about physics.
The possibility of a universe with hidden dimensions, and maybe a single theory explaining it all. It's just awe-inspiring, isn't it? It really makes you think about the deep mysteries we explore here on Cosmic Origins Revealed.
It does. The quest to understand the fundamental fabric of reality is ongoing, and string theory, for all its challenges, remains a really compelling and exciting part of that quest.
Well, we hope this deep dive into the weird and wonderful world of string theory right here on Cosmic Origins Revealed has sparked your curiosity about these cosmic puzzles.
It's a journey into the very small and possibly the very many dimensions.
If you're captivated by the universe's deepest secrets, definitely check out our YouTube channel, Cosmic Origins Revealed, for more mind-expanding explorations. Join our community of curious minds.